The world is quantum, and no one knows why. This is not the strangeness most people mean when they use the word. It is older and stranger, and more difficult to look at directly. At the deepest level any experiment has ever reached, the universe does not behave like the universe we appear to live in. It behaves like something else, something that does not have definite properties until something forces it to choose. Physicists have known this for more than 120 years. The mathematics that describes it has never failed a single experimental test. Every prediction it has made, when measured with sufficient precision, has been confirmed. Not in some laboratories, in all of them. Not by some research groups, by all of them. Every transistor in every machine ever built is a working artifact of this theory. Every laser in every room, every chemical bond in the body that is now breathing. And yet, and this is the part that almost no one says clearly, no one can tell you why the world is this way rather than another way. Why is the world quantum? That is the question that opens here, and that does not close. Not how the mathematics works. The mathematics works, not what the experiments show. The experiments are clear. Why this? Why this particular shape of reality, when so many other shapes were available? Why probability instead of certainty? Why entanglement instead of separation? Why the act of measurement is a kind of participation rather than a passive reading of what was already there? For most of the 20th century, this question was considered impolite. The mathematics worked. The predictions held. To ask what any of it meant was a sign that one was not a serious physicist. There was a phrase that became almost a creed in certain departments. The phrase was, "Shut up and calculate." It was attributed to several people. It captured a real attitude. Whatever the world is doing, do not ask why. That silence has broken. Slowly. It broke first in 1964, when a quiet Irish physicist named John Bell wrote a 4-page paper that almost no one read at the time. It broke again in 1982, when a French experimentalist named Alain Aspect performed a measurement that confirmed what Bell's paper had predicted. It broke decisively in 2015, when 3 independent groups in Delft and Vienna and Boulder closed every remaining experimental loophole at once. And it broke into public consciousness in 2022, when Aspect and 2 of his successors received the Nobel Prize for work that the physics community had quietly avoided thinking about for decades. The result is not in dispute. The world cannot be both local and real in the way classical physics required. One of those words has to give. The universe has answered which one, and the answer is not yet fully understood. There is a phrase that has become common in certain corners of the culture. The phrase is that quantum physics has proved something, proved that consciousness creates reality, proved that we manifest what we focus on, proved that the universe responds to our thoughts. The phrase is not accurate. It belongs to a marketplace that needs the strangeness of physics to sell something. The actual claim physics is making is stranger than the marketplace version, and less useful, and less comforting. It will not help you find a parking space. It will not bend the outcome of a job interview. What it suggests is something the marketplace cannot resell, because the marketplace cannot package it. What it suggests is that the objects in the world do not have the kind of independent existence that classical intuition assigns them. They are not small billiard balls with their properties tucked safely inside, waiting to be discovered by a measuring device. They are something else. The closer the experiment looks, the less they look like things, and the more they look like relations. Relations of what to what. This is the part no one knows. And here, very faintly, the older voices begin to be audible behind the equations. Long before there were experiments to perform, certain figures in certain traditions sat with the question of what kind of thing the world is. They did not have laboratories. They had attention. They had decades. They had practices that turned the mind into an instrument fine enough to register what coarser instruments could not. Some of them, not all of them, not most of them, but a few of them in lineages that have transmitted their work for more than 1,000 years, arrived at descriptions of reality that physics is only now beginning to circle from the outside. The languages are different. The methods differ. The pattern they describe is, strangely, the same shape. This convergence is dangerous to speak about. It is dangerous because it invites the cheap version, the breathless version, the version that says ancient wisdom predicted modern science. That version is false. The contemplatives were not doing physics. The physicists are not doing contemplation. The instruments cannot be compared. The claims cannot be translated into each other without distortion. What is true is something more subtle and more disturbing than the cheap version. Two completely different methods applied to the same reality from opposite ends of human investigation have circled the same structural fact. Not the same claim, the same shape, a shape in which the things are not really things, in which the separations are not really separate, in which the asking and the answer are not as cleanly distinguishable as the language we use would prefer. There is a research program, almost unknown outside professional physics, called quantum reconstructions. It began with a paper by a British physicist named Lucien Hardy in 2001. The paper had a strange title. It was called Quantum Theory from 5 Reasonable Axioms. What Hardy did, and what others have refined since, Giulio Ciribella and his collaborators in Italy, Luis Massanes and Marcus Müller working in Europe, was to ask whether the strange axioms of quantum mechanics could be derived from simpler principles about how information must behave in any consistent universe. The work is technical. The result, in plain language, is this. Quantum mechanics may not be an arbitrary theory invented to fit the data. It may be the only kind of theory possible. The strangeness is not strange. It is forced. Given a small set of reasonable principles about distinguishability and composition and continuity, the universe must be quantum. If this is correct, and it is not yet certain, and there are open technical questions, then a different kind of vertigo opens beneath the question we began with. The question is no longer, why is the world quantum, as if the world had been free to be otherwise and made a curious choice? The question becomes, why is the world the kind of thing in which information behaves the way it does, such that everything else follows? This is a different question. It is older. It is the question that has been asked, in a different vocabulary, for at least 2,000 years. What is real? What is being? What is the structure of what is? The first thing that has to be said is that we do not know. The second is that what we know is enough to make the not knowing precise. A structure of mathematics and experiment has been built across the past century that locates exactly where the ignorance lies. We can point to it. We can write equations whose interpretation no one understands. We can run experiments whose outcomes we predict perfectly without being able to say what the outcomes mean. The ignorance is sharp. The mystery has edges now. There is a particular kind of stillness that arrives when a calculation closes. The notebook is set down. The lamp is on. The equation has been verified to 14 decimal places, and the verifier stares at the wall, knowing the equation works and not knowing why. This stillness is not loneliness. It is something else. It is the stillness of standing in front of a fact whose meaning is older than the fact. There is another stillness that arrives at the end of a long sitting, when even the question dissolves, and what is left is not an answer, and not a void, and not any of the words that have been tried for it across centuries. These two stillnesses are not the same. They may be neighbors. The room you are in is not as empty as it appears. The body that is breathing is composed of structures that are doing, right now, the strange things this question is about. The vacuum beneath the floor is humming with what physics calls virtual particles, with a fabric that is not nothing and not quite something either. The chair that holds your weight is held together by forces that, when examined closely enough, dissolve into the same open question. The world is quantum. The asking continues, and the question has been older than the answer for so long that it begins to seem, in certain quiet hours, that the question may be the shape of the answer, that the not knowing is not a gap to be closed, but the ground on which everything that has ever been known has stood. The history of how this not knowing entered physics is shorter than the history of physics itself. It begins in Berlin in the final weeks of the 19th century with a man who did not want to be the one to begin it. Before 1900, the structure of classical physics had appeared, to most working scientists, essentially complete. Newton's mechanics described the motion of matter. Maxwell's equations describe the behavior of electric and magnetic fields. Thermodynamics describe the statistical behavior of large collections of particles. There were small problems remaining. What Lord Kelvin had famously called two small clouds on the horizon. But the consensus among most physicists was that the broad picture was finished. The world was a smooth, deterministic clockwork, and the work that remained was to refine the precision of the measurements and to clean up the small clouds. One of those clouds was the radiation emitted by a heated object. The other was the failure to detect the motion of the Earth through the supposed luminiferous ether. Both clouds, by the end of the next decade, would turn out to be storms. The second cloud broke open into relativity. The first cloud broke open into quantum mechanics. The breaking of the first cloud is where this part of the story begins. Max Planck, the Berlin professor who would later call his own discovery an act of desperation, was working on a problem that had become embarrassing for 19th century physics. The problem was the radiation emitted by what physicists called a black body, an idealized object that absorbs and re-emits energy. The classical predictions for how this radiation should be distributed across the spectrum disagreed with the measurements. They disagreed catastrophically. At short wavelengths, classical theory predicted that the energy radiated should rise without limit toward what came to be called the ultraviolet catastrophe. The world, classical physics said, should be radiating infinite energy at every moment. It was not. Something was wrong. Planck found a formula that fit the data. He fit it first by inspired guessing, and only afterward sought a derivation. The derivation he found was a kind of forced trick. He had to assume that radiation was emitted not as a continuous stream, but in discrete packets, that the exchange of energy between matter and the electromagnetic field was quantized, in units proportional to the frequency of the radiation. The proportionality constant he introduced is now called Planck's constant. It is one of the small numbers that determine the fabric of the world. The equation worked. The data fit. The classical edifice cracked. Planck himself did not believe in what he had done. He spent the next 15 years trying to find a way to derive the same result without the quantum. He failed. The universe, it seemed, did not need his permission to be discrete at its foundation. He had introduced the seed of the new physics as a man trying to defend the old physics. He would spend the rest of his life uneasy about the consequences. What Planck had introduced as a mathematical convenience, Einstein took seriously. In 1905, a 26-year-old patent clerk in Bern produced 4 papers in a single year that would reshape physics. One of them addressed a phenomenon called the photoelectric effect, the way light, when it strikes a metal surface, knocks electrons loose. The classical theory of light as a continuous wave could not explain the way the effect actually worked. The energy of the ejected electrons depended on the frequency of the light, not its intensity. Einstein's solution was to propose that Planck's quanta were not a mathematical trick. They were real. Light itself, he argued, comes in discrete packets, what we now call photons. The proposal was widely resisted. For nearly 2 decades, most physicists found it untenable. Robert Millikan, the American experimentalist who confirmed Einstein's quantitative predictions about the photoelectric effect in 1916, called the underlying theory wholly untenable, even as his own data supported it. The data won. Slowly. In 1921, Einstein was awarded the Nobel Prize. Not for relativity, which most of his contemporaries considered too speculative, but for this paper on light quanta. The discreteness was no longer just a feature of how matter absorbs and emits radiation. It was a feature of the radiation itself. Light, the most continuous thing the classical mind could imagine, was not continuous. It was particulate, and in certain experiments, it was wave-like. It was both, depending on what was asked of it. This was the first hint of what came to be called the wave-particle duality, the strange double face of the quantum world. The cracks were widening, not because anyone wished them to, because the data forced them open. The cracks held for 2 decades. The Bohr model of the atom in 1913 patched the structure with quantized orbits, but it was a patch on a wall that was failing. By the mid-1920s, the wall had collapsed. In the summer of 1925, a 23-year-old German physicist named Werner Heisenberg was on the island of Helgoland in the North Sea, recovering from hay fever. He had taken with him the problem of the spectrum of hydrogen, the precise frequencies of light that hydrogen atoms emit. While the wind moved across the rocks and the sea, he worked out a strange new mathematics. The mathematics did not describe the position of an electron or its orbit, or any picture the classical mind could form. It described only the observable transitions between energy states. The quantities he wrote down did not commute. The order in which they were multiplied mattered. He did not yet recognize what he had. Max Born, his older colleague at Göttingen, recognized it within weeks. The mathematics Heisenberg had stumbled onto was matrix algebra. Born and Pascual Jordan formalized it. The first complete theory of quantum mechanics was born. Within months, working independently in the Alps, a 40-year-old Austrian physicist named Erwin Schrödinger produced an entirely different mathematics. His was a wave equation, a continuous partial differential equation describing what he initially believed was a real, physical wave of matter. The two mathematics could not have looked more different. One was discrete and matrix algebraic. The other was continuous and wave mechanical. And yet, within the year, Schrödinger himself proved they were equivalent. Two completely different formal structures, two completely different intuitions about what the world is, produced the same predictions about every measurement. What did the predictions describe? This was the question Max Born answered in 1926, in a paper whose footnote contained the answer. The wave function did not describe a physical wave of matter. It described a wave of probability. The square of its amplitude gave the probability of finding the particle at a given location upon measurement. The mathematics had become statistical at the foundation. And then, in 1927, Heisenberg published a paper that named the limit. The position and momentum of a particle cannot both be known to arbitrary precision. The product of the uncertainties has a lower bound. This was not a limitation of measuring devices. It was a feature of the world. The world at this scale did not have definite simultaneous properties to be measured. It had structures of probability. By the autumn of 1927, the founders of the new physics gathered for the 5th Solvay Conference in Brussels. The photograph from that conference shows 29 of the most important physicists of the 20th century. 17 of them would, in time, receive the Nobel Prize. In that room, in those days, the form that the new physics would take was negotiated. The result of those negotiations is now called the Copenhagen interpretation, after the city where Niels Bohr had built the institute that hosted much of the work. The interpretation was less a single doctrine than a discipline of restraint about what could and could not be said. The wave function describes the system. Measurement causes what Bohr called a collapse or actualization. The classical world of definite properties exists for the measuring apparatus. The quantum world of superposed possibilities exists for the system being measured. Between them, somewhere, runs what Werner Heisenberg later called the cut, the boundary between the world that has properties and the world that does not. Where exactly the cut runs, Bohr did not say. He could not say. The mathematics of quantum mechanics is reversible and continuous. The act of measurement in the standard formalism is irreversible and discontinuous. There is a moment in the formalism where the smooth evolution of the wave function gives way to a sudden choice of outcome, and no equation in the theory describes what happens in that moment. This was the measurement problem. It was implicit in the formalism from the beginning. It has been there ever since. Most working physicists, then and now, set the problem aside. There was, in certain departments, an attitude that became almost a creed. Calculate the predictions. Compare them to the experiments. Do not ask what any of it means. The phrase was, shut up and calculate. The phrase appears to have been coined by the American physicist David Mermin in 1989, but it captured an attitude that had been operative for 60 years. The mathematics worked. The world cooperated. Asking why was thought to be unprofessional. There was one physicist who refused to set the question aside. In 1935, working at the Institute for Advanced Study in Princeton with two younger colleagues, Albert Einstein produced a paper that would change the trajectory of the question, though not for nearly 30 years. The paper appeared in the journal Physical Review in May of that year. The three authors were Einstein, Boris Podolsky, and Nathan Rosen. The paper is known by their initials. EPR. What Einstein and his colleagues showed was this. Quantum mechanics permits a kind of state, what is now called an entangled state, in which two particles can be prepared together and then separated by any distance, and in which a measurement of one particle determines instantly what a measurement of the other will reveal. The correlations between the two measurements are stronger than any classical mechanism could produce. If quantum mechanics is correct and complete, then either the two particles are somehow communicating faster than light, which violates relativity, or they did not have definite properties before the measurement, which violates a deeper intuition that the world exists independently of being looked at. Einstein called this second possibility, with quiet contempt, spooky action at a distance. He did not believe it. He thought it showed that quantum mechanics must be incomplete, that there must be hidden variables, deeper properties of the particles that the theory had not yet discovered that would restore locality and realism. Niels Bohr replied in the same journal a few months later. His reply was technical and famously difficult to follow. The argument was not resolved. It was simply parked. The standard response among working physicists was to call the EPR paper a philosophical disagreement and return to the calculations. For nearly 30 years, the question lay nearly dormant. It was a kind of philosophical puzzle that could not be tested. The mathematics worked. The experiments confirmed the mathematics. The deep question of what the world was beneath the working mathematics was deferred. The deferral lasted until 1964. In that year, working at CERN in Geneva on the unrelated problem of particle accelerator design, an Irish physicist named John Stuart Bell published a short paper in a small journal that has since gone out of print. The journal was called Physics. The paper was 4 pages long. It was titled On the Einstein-Podolsky-Rosen Paradox. It was barely read at the time. Bell himself wrote it on the side of his official work. He thought of it as a kind of intellectual hobby. He did not know he had just changed the trajectory of foundational physics. What Bell did was to take Einstein's intuition that there must be hidden variables restoring local realism, and to ask what predictions such a theory would have to make. Any theory in which physical properties are local, in the sense that what happens here does not depend on what is done over there, and real, in the sense that the properties exist before they are measured, must satisfy certain mathematical constraints on the correlations between distant measurements. Bell wrote those constraints down. The constraints are now called Bell's inequality. The strangeness was this: quantum mechanics predicted that the inequality could be violated. The hidden variable theories Einstein hoped for could not violate it. So the question of which view of the world was correct was no longer philosophical. It was experimental. Build the apparatus, measure the correlations, see whether the world satisfies the inequality or violates it. Bell himself initially hoped, for reasons of physical intuition, that the experiments would confirm Einstein's view. He was, in a quiet way, a closet realist. He thought spooky action at a distance was too much to ask of nature. He was wrong. The first practical test came in 1972, when John Clauser and Stuart Friedman, working at the University of California, Berkeley, used pairs of correlated photons emitted from calcium atoms and measured the correlations between their polarizations at different angles. The inequality was violated. The result agreed with quantum mechanics. It disagreed with any locally real hidden variable theory. Einstein, who had died in 1955, was on the losing side of the question he had asked. But the 1972 experiment contained loopholes. Every Bell test does at first. The loopholes were technical imperfections, undetected photons, fixed measurement angles, timing windows that allowed a committed defender of local realism to argue the result was not yet decisive. The next 40 years were spent closing them, one by one. There is a particular quality to the quiet of a laboratory at 3 a.m. The hum of the cooling pumps, the faint click of the photon counters, the screen that is still showing the result of the run that finished 6 hours ago, the researcher who is not yet ready to go home. This is the room in which the question was answered, not in a single moment, in thousands of moments, over 50 years, across continents. Through the 1970s and into the 1980s, the experiments became more careful. The decisive series began in 1981 in the southern suburbs of Paris, at the Institut d'Optique in Orsay, where a French experimentalist named Alain Aspect performed a sequence of measurements that closed one of the most important loopholes. Aspect introduced a clever modification. The orientation of the polarization analyzers was switched rapidly, while the photons were already in flight between the source and the detectors. This meant that the choice of what to measure on one side could not have been communicated to the other side without exceeding the speed of light. The locality loophole, in its strongest form, was closed. The inequality was still violated. The agreement with quantum mechanics held. Through the 1990s and 2000s, groups in Geneva and Innsbruck and elsewhere refined the experiments further, using longer baselines, faster switching, more efficient detectors. Each new result narrowed the room for any locally real alternative. By the early 2000s, only the most stubborn loopholes remained. They could be closed in principle. The question was when, and by whom? In the autumn of 2015, 3 independent groups answered the question almost simultaneously in 3 different countries. The first result came from Delft, in the Netherlands, where a team led by Ronald Hansen at the Delft University of Technology used pairs of nitrogen vacancy centers in diamond, atomic defects that can be prepared in entangled states. The 2 diamonds were placed in laboratories on opposite sides of the campus, separated by 1.3 kilometers. The detection loophole and the locality loophole, the 2 great remaining gaps, were closed in the same experimental design. The result was published in Nature in October of 2015. The inequality was violated by a margin that excluded local realism at very high confidence. Within weeks, results from 2 other groups followed. At the Institute of Quantum Optics and Quantum Information in Vienna, a team led by Anton Zeilinger, with Marissa Justina as lead author, performed the equivalent test using entangled photons and high-efficiency detectors. At the National Institute of Standards and Technology in Boulder, Colorado, a team led by Lyndon Shalm did the same. Both confirmed the Delft result. All 3 published within a few months of each other. The inequality was violated. Every major loophole had been closed. A century of debate about whether the strangeness of quantum mechanics was a sign of the world's incompleteness or a real feature of the world had been settled by the data, not in favor of Einstein, in favor of the strangeness. The world is not locally real in the classical sense. Either signals are propagating faster than light in ways no experiment has been able to detect, or properties do not exist independently of measurement or some deeper assumption embedded in the classical worldview. The assumption that experimenters freely choose what to measure. The assumption that the past determines the future and not the reverse. The assumption that there is a single observer independent reality at all has to be abandoned. One of these things has to give. The data does not tell us which one. This is the part of the story most popular accounts do not emphasize. The Bell tests do not tell us that the world is simply non-local. They tell us that some classical assumption fails. Which one is a matter of interpretation, and the field has not converged on an answer. And then, between 2017 and 2018, a small group of physicists, including Andrew Friedman, David Kaiser, Alan Guth, and Anton Zeilinger, extended the test one step further. They wanted to close a remaining loophole, the freedom of choice loophole, the possibility that the measurement settings on the 2 sides might be subtly correlated with the hidden variables of the system. To do this, they used light from quasars, the most distant objects in the universe, to randomize the measurement settings. The light from those quasars had been traveling for billions of years before arriving at the laboratory. Any correlation between the measurement settings and the source would have to have been established before the formation of the solar system, probably before the formation of the galaxy. In the most extreme run, with quasars more than 7 billion light-years away, before there was an Earth at all. The inequality was still violated. The result held. In October of 2022, the Nobel Prize in Physics was awarded jointly to Alan Aspect, John Clauser, and Anton Zeilinger. The citation read, "For experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science." The award was, in part, a quiet acknowledgement that work the physics community had once treated as philosophical or marginal was in fact among the most important experimental work of the late 20th century. The Nobel Committee said what it could say in a sentence of citation. What it did not say, and could not say, is what the result means. There are decades in physics during which nothing fundamental shifts. The instruments improve. The precision deepens. The mathematics is refined. And then there are decades, though they are usually only recognized in retrospect, during which the ground itself moves. The decade between 2015 and 2025 has been one of those. The world that physics now describes is not the world of Newton. It is also not quite the world of Bohr. It is something stranger, and the strangeness is no longer in dispute. There is one remaining piece of the foundation that must be set in place. It is the part of the story most popular accounts handle badly, because it sits in a peculiar space, neither a solution to the measurement problem nor a dismissal of it. The piece is called decoherence theory. It was developed primarily in the 1970s and 1980s by a small group of physicists working on the foundations of quantum mechanics, most notably the German physicist Heinz-Dieter Zeh, who first articulated the concept in a 1970 paper, and the Polish-American physicist Wojciech Zurek at Los Alamos, who developed its mathematical structure through the following decades. What decoherence theory shows is this. The reason we do not see Schrödinger's cat in a superposition of alive and dead is not because some mysterious measurement collapse has occurred. It is because the cat is constantly interacting with its environment, air molecules, photons, thermal radiation, and these interactions rapidly entangle the cat's quantum state with the state of the environment. The interference between the alive and dead branches becomes, for any practical observer, undetectable. The classical world we appear to inhabit emerges from this rapid environmental entanglement. Decoherence is real. It is mathematically rigorous. It has been confirmed in many experiments, most famously by Serge Haroche's group in Paris in the 1990s, work that earned him a share of the Nobel Prize in 2012. And it explains a great deal that the founders of quantum mechanics could not explain. It explains why we see a classical world at the scale of everyday life. It explains why the wave-like properties of large objects are invisible. It explains the appearance of definite outcomes. But decoherence does not explain why we see one outcome rather than another. The mathematics still describes a superposition, only now the superposition is between branches in which the cat is alive and the environment registers alive, and branches in which the cat is dead and the environment registers dead. Both branches are in the equations. Both branches evolve unitarily. The fact that a single observer encounters only one branch is something decoherence does not account for. This is the measurement problem at its core. Decoherence reduced it. It did not solve it. Anyone who says decoherence has solved the measurement problem is either being loose with the language or is using a particular interpretation, usually some form of many worlds, in which the unobserved branches are taken to be real. The interpretation is not forced by the mathematics. The mathematics is silent on it. And so, by the second decade of the 21st century, the historical foundation has been set in place. The world is quantum. The world is not locally real in the classical sense. The mathematics that describes it has never failed a predictive test. The classical world emerges from the quantum substrate through decoherence in a way that explains the appearance of definite outcomes without explaining the actual selection of any one of them. The measurement problem is open. It has been open for 90 years. The major interpretations of quantum mechanics, and there are at least half a dozen serious ones, all reproduce the same experimental predictions and disagree about what the world is. This is what the foundation gives. It is not nothing. It is a structure of mathematics and experiment more precise than any field of human inquiry has ever produced. It is a precise location for the ignorance, and it is, when looked at carefully, the beginning of a much deeper question. Not what is the world made of, but why is the world the kind of thing in which what we call making sense breaks down at the threshold? And yet the standard story does not close. The mathematics works. The experiments confirm. The world has been measured to a precision that would have been unimaginable to the founders of the field. And in the middle of that precision, in the very heart of the formalism, sits a problem that has not been solved for nearly 100 years. It is called the measurement problem. The name is technical. The problem is not. The problem is this. The mathematics of quantum mechanics describes the state of a physical system as a wave function, a smoothly evolving structure that can hold many possibilities at once. As long as the system is left undisturbed, the wave function evolves according to a single equation, the Schrödinger equation, in a way that is fully deterministic and fully reversible. There is no randomness in this evolution. There are no choices. The wave function flows, and then a measurement is made, and the wave function somehow selects a single outcome. The other possibilities present a moment before are gone. The mathematics that describe the smooth evolution does not describe this selection. The equations are silent on it. A second formal rule has to be added by hand to describe what happens when an observer interacts with the system. This second rule is irreversible, discontinuous, and probabilistic. It contradicts the first rule. It cannot be derived from the first rule. It is simply imposed. This is the measurement problem. It is not a problem of interpretation. It is a problem in the formalism itself. Two incompatible dynamical rules. The theory tells us when to use which one. It does not tell us why. There is a phrase that physicists who work on the foundation sometimes use to describe what this problem feels like from the inside. The phrase is, the central scandal of physics. Sean Carroll, the American theoretical physicist at Johns Hopkins, has used it in print. Tim Maudlin, the philosopher of physics at NYU, has used it. So have others, often more quietly, in seminar rooms and late-night conversations. The scandal is not that the problem is unsolved. The scandal is that for 60 years it was considered impolite to even acknowledge it as a problem. Decoherence has changed the texture of the problem without changing its core. It explains why the wave-like properties of large objects are not observed. It explains why the world looks classical at the scale of everyday experience. It explains the appearance of definite outcomes. What it does not explain is why a particular outcome is the one we encounter. The mathematics still contains all the branches. Decoherence renders them mutually invisible. It does not erase any of them. You have, perhaps, watched a coin spin on a table. The coin will land. It will land heads or tails. The mathematics of quantum mechanics, applied carefully, would say that the wave function of the coin contains both outcomes, heads and tails, both still present after the coin has come to rest. The fact that you see heads and not tails is something the equations do not explain. This is not a poetic flourish. It is the precise content of the problem. The honest position is this: quantum mechanics works. Quantum mechanics has never failed. And quantum mechanics, as it stands, does not describe what is actually happening when a single outcome appears in the world. 90 years of work has refined the question. None of it has answered it. And so a different kind of work began, in earnest, in the 1950s and has continued ever since. The work was not to discover new experimental predictions of quantum mechanics. The predictions are what they are. The work was to find a story about the world that the equations could be a description of. The stories are called interpretations. There are, at this point, at least half a dozen serious ones. The first major alternative to the Copenhagen view was proposed in 1957 by Hugh Everett, a graduate student at Princeton working under John Wheeler. Everett proposed that the wave function never collapses at all. The smooth evolution continues. When a measurement occurs, the universe itself branches. The observer who saw heads and the observer who saw tails are both real in different branches of a single, vastly larger wave function. This view is now called the many worlds interpretation. The popular version of it, in which infinite parallel universes contain every possible outcome of every choice, is a simplification. The actual proposal is more careful and more austere. It does not require new physics. It requires only that the Schrödinger equation be taken at face value all the way down. There is another view, developed in 1952 by David Bohm, and earlier in a different form by Louis de Broglie. In this view, particles do have definite positions at all times. The wave function exists as a real field that guides them, a kind of pilot wave. The randomness of measurement is, in this view, only apparent. The world is fully deterministic. The hidden variables Einstein hoped for exist after all. The cost is that the pilot wave is explicitly non-local. What guides one particle depends instantaneously on the state of all other particles. This view reproduces every prediction of standard quantum mechanics. It has never gained majority acceptance, partly for technical reasons and partly because the explicit non-locality was, for many, harder to accept than the standard formalism. There is a third view, proposed in 1986 by Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber. In this view, known as GRW, or objective collapse, wave functions really do collapse, but they do so spontaneously, without any reference to observation. The collapse happens at random times, with very low probability for small systems and very high probability for large ones. This makes the theory experimentally distinguishable from standard quantum mechanics. So far, the experiments have constrained the parameters of GRW, but have not ruled it out. There are others. Roger Penrose, the British mathematical physicist, has proposed that gravity itself causes collapse. Carlo Rovelli, the Italian theorist, has proposed a relational interpretation in which the wave function describes not the world, but a particular system's relationship to another system. There is the consistent histories approach. There is cubism, which we will come to in a moment. All of these interpretations reproduce, exactly, every experimental prediction of standard quantum mechanics. None has converged. The choice between them is not empirical. It is, at this point, a choice between visions of what kind of world we live in. There is something curious about being in a field that has produced the most precise predictions in the history of science, and that cannot agree on what those predictions are predictions of. The mathematics is shared, the experiments are shared, the data are not in dispute. What is in dispute is the world the data describe. Whole careers have been spent in seminar rooms and journal pages trying to settle this. The settlement has not come. And then, in 2018, two physicists at the Swiss Federal Institute of Technology in Zurich published a result that disturbed the foundations again. The physicists were Daniela Frauchiger and her advisor, Renato Renner. The paper appeared in Nature Communications. It was titled, with academic understatement, "Quantum theory cannot consistently describe the use of itself." What Frauchiger and Renner proved was this. Consider a scenario involving multiple observers, each performing measurements according to standard quantum mechanics, each also being capable of describing what the others observe using the same quantum formalism. If we require that the formalism applies universally, that observers and laboratories are also quantum systems, and that all observers reach consistent conclusions about the world, and that the standard rules for assigning outcomes to measurements hold, then a contradiction arises. One of these assumptions has to fail. The paper is technical. The argument is rigorous. What it shows, in plain language, is that no single observer-independent reality, consistent with the universal applicability of quantum mechanics, can exist. Either the formalism does not apply universally, some systems are special, some are not, or different observers can be holding mutually contradictory but equally valid descriptions of the same event, or the standard rules for assigning probabilities to outcomes fail in some cases. There is no fourth option that survives the argument. This was a result no one had expected. The reaction in the Foundation's community was something between alarm and exhilaration. Papers responding to Frauchiger-Renner are still being written years later. Some interpretations of quantum mechanics, particularly those that posited a single observer-independent reality, have had to retreat or substantially modify their claims. Other interpretations, those that already accepted the loss of observer independence, were vindicated. The result has not been refuted. It has been refined. It has been generalized. The conclusion remains. Whatever quantum mechanics is telling us about the world, it is not telling us that there is a single objective reality that all observers can, in principle, agree about. That picture, after 120 years, has finally and rigorously been ruled out. There is another line of work, less well known to the public, that has been quietly approaching the same wall from a different direction. It began with a paper we have already touched on, the British physicist Lucian Hardy. Then at Oxford, published in 2001, a paper called Quantum Theory from 5 Reasonable Axioms. The paper asked a question that had not been seriously posed before. Can the strange axioms of quantum mechanics be derived from simpler principles, principles that any consistent operational theory of physics would have to satisfy? Hardy found that they could be, almost. His 5 axioms about how distinguishable states compose, how information is preserved, how probabilities behave, produced quantum mechanics uniquely, except for a small ambiguity that he addressed by adding a continuity assumption. The result was that quantum mechanics is not, as it had appeared for a century, an arbitrary mathematical structure that just happens to fit the data. It is the unique theory satisfying a small set of operational principles. The program The program continued. In 2011, three theorists in Italy, Giulio Ciribella, Giacomo Mauro Dariano, and Paolo Perinotti, proved a stronger result, deriving quantum mechanics from purely informational principles, including a principle of purification that captured the essential role of entanglement. Luis Massanes in Barcelona and Marcus Müller in Vienna, working separately and together, refined the program further. The work is technical. It is rarely covered in popular accounts. Its implications are striking. If the reconstructions are correct, the question that has been opening here, why is the world quantum, receives an unexpected partial answer. The world is quantum because any consistent universe in which information behaves the way information appears to behave must be quantum. The strangeness is not strange. It is forced by the structure of information itself. This does not solve the measurement problem. It does not resolve the question of what reality is doing. What it does is to shift the question one level deeper. The question is no longer why these axioms. The question becomes, why is the world the kind of place where these informational principles obtain? That question is older than physics. There is a phrase, much older than quantum mechanics, for the kind of question that grows deeper the more carefully you ask it. The phrase is not important here. What matters is that physics, by its own internal logic, has arrived at such a question, not through speculation. Through the working out of the mathematics. The wall is the same wall. The question is older than the wall. There is one interpretation of quantum mechanics that goes further than the others in accepting what the reconstructions and Frauheger-Renner suggest. It is called cubism, short for quantum Bayesianism. Its principal developers are the American physicists Christopher Fuchs, David Mermin, and Rüdiger Schack. The view emerged in its current form in the early 2000s. Cubism makes a radical proposal. The wave function, in this view, is not a description of the world. It is a description of the beliefs of an agent about what the agent will experience when the agent acts upon the world. The probabilities the wave function generates are not probabilities of objective events. They are degrees of personal belief, mathematically constrained by the structure of quantum theory. This sounds at first like solipsism. It is not. The agent is not making the world. The agent is acting within a world that responds in lawful but irreducibly statistical ways. What cubism denies is that there is a single, observer-independent state of the world that the wave function describes from outside. The wave function is in the relationship between agent and world. It is not in the world. Cubism makes one prediction that distinguishes it from many other interpretations. It says that the world genuinely is participatory at the foundation, that the act of asking a question of the world is not separate from the world's reply. This is the view that John Wheeler, the American physicist who named the black hole and was the doctoral advisor of both Hugh Everett and Richard Feynman, articulated in his later years under the phrase, the participatory universe. Wheeler thought that observation was not a passive reading of what was already there. He thought it was, in some deep sense, the world's way of bringing forth what would otherwise have remained unresolved. This is not the popular version in which thoughts cause outcomes. It is something stranger. It is the proposal that the asking and the answering are not as cleanly separable as the classical mind has always assumed. Wheeler took the proposal further in the last decades of his life. In a series of papers in the 1980s and 1990s, he proposed that information may be more fundamental than matter. His phrase was, it from bit. Every physical thing, every it, every particle, every field, derives its existence, in Wheeler's view, from binary answers to yes or no questions. The questions are posed by measurement. The answers, accumulated, are the world. The proposal sounded speculative when he made it. It sounds less speculative now. The reconstructions program has shown that quantum mechanics may follow uniquely from informational principles. Recent work in quantum gravity has begun to suggest that space-time itself may emerge from entanglement, the substrate beneath the substrate, if there is one, looks from this vantage less like matter and more like information. What that means, no one knows. In 2013, two of the most accomplished theoretical physicists of the past half-century proposed a conjecture that, if true, would unite two of the strangest results in physics into a single phenomenon. The physicists were Juan Maldacena at the Institute for Advanced Study in Princeton and Leonard Susskind at Stanford. The conjecture is called ER equals EPR. The name encodes two papers. ER is for the 1935 paper of Einstein and Nathan Rosen on what came to be called Einstein-Rosen bridges, or wormholes, non-traversable connections through space-time predicted by general relativity. EPR is for the same year's Einstein-Podolsky-Rosen paper on quantum entanglement. For most of the 20th century, these two phenomena were thought to have nothing to do with each other. One was a feature of classical geometry. The other was a feature of quantum statistics. What Maldacena and Susskind proposed is that they are the same thing. Every entangled pair of particles in their conjecture is connected by a tiny non-traversable wormhole, a thread of geometry linking them through a dimension we cannot see. The wormhole cannot be used to send signals. It does not violate relativity, but it provides a geometric explanation for why entangled particles are correlated in ways no classical mechanism could produce. The correlations are not action at a distance. They are the geometry of a connection that does not pass through the intervening space. The conjecture is not proven. It is a research program. There is real progress in showing that, at least in certain mathematical contexts, the equivalence holds. Whether it holds in the actual universe remains an open question. The program has changed how foundational physics thinks about the relationship between space, geometry, and information. If ER equals EPR is correct in some form, then the space we move through is not the empty stage of classical physics. It is woven from the same fabric as the correlations that violate Bell's inequality. The geometry of the world and the entanglement of its parts are not two things. They are one thing seen from two angles. And there is one more anomaly that the Foundation has not absorbed that signals how deep the missing piece must be. It is sometimes called the worst prediction in the history of physics. It is the cosmological constant problem. When quantum field theory is used to estimate the energy density of the vacuum, the energy of empty space, arising from the constant fluctuations of the quantum fields that fill it, the prediction is enormous. When the same energy density is measured cosmologically by observing the expansion of the universe, the value is incomparably smaller. The discrepancy is roughly 1 followed by 120 zeros. The most successful theoretical structure in physics produces, for one of the simplest possible quantities, an answer that is wrong by a factor larger than any factor in human knowledge. No one knows how to resolve this. The mismatch is a signal, a very loud signal, that the way we currently calculate the vacuum is missing something fundamental. The empty space around you hides a problem of this size. There is a kind of quiet that arrives in physics now, in the foundational seminars where these results are presented. It is not the quiet of consensus, it is the quiet of recognition that no one in the room knows. The mathematics is on the board. The experiments are reproducible. The interpretations are arrayed like positions on a battlefield with no decisive engagement in sight. And in that quiet, the older question begins, very faintly, to be audible again. What kind of thing is this world that we have been describing all along? This is the honest position of physics after 125 years. What is established is the formalism, the wave function, the Schrödinger equation, the rules of measurement, the violation of Bell's inequality, the emergence of classical behavior through decoherence. All of this is not in dispute. The mathematics has never failed. What is suggested by the reconstructions and by Frauchiger-Renner and by the development of cubism is that the world at its foundation is not made of things with intrinsic properties standing in classical relations. It is made of something else, something more relational, something that information, rather than substance, may be a better word for, something that the act of observation does not passively register, but somehow participates in. This is suggested. It is not proven. What remains unknown is what the world actually is. The interpretations of quantum mechanics, considered carefully, are not just different stories. They are different proposals about the fundamental nature of reality. The mathematics is consistent with all of them. The experiments distinguish only some of them. The full question, what is being, what is the structure of what is open. This is not a failure of physics. It is a strange kind of achievement. A field has been built that locates exactly where the ignorance lies, that names exactly what the open questions are, that has reduced the space of possible answers to a small number of well-defined positions, and that admits, when pressed, that it has not chosen between them. The room you are in is, at the foundation, doing one of these strange things. The breath that is moving is, at the foundation, made of structures whose nature is in question. The asking is not separate from the asked, and the question, what is real? What is being? What is the structure of what is? Has been asked from another direction, by another method, by other inquirers, for at least 2,500 years. They did not have the equations. They did not have the laboratories. They had something else. And what they found, beneath the surface of what they have been understood to have said, is closer to the structure that physics has stumbled onto than almost anyone outside both fields has noticed. The convergence is not a coincidence to be celebrated. It is not a proof to be displayed. It is, when examined carefully, a structural fact about what happens when human attention, applied carefully for a long enough time to the question of what reality is, arrives at certain shapes. 4 traditions separated by thousands of miles and thousands of years, with no contact between them, with no possibility of borrowing one another's vocabulary, arrived at descriptions of reality that share an architectural pattern. None of them was doing physics. None of them had access to the mathematics that could express what they were articulating. They had attention. They had practice. They had transmission across generations, and what they produced, when stripped of the cultural surface, looks strangely like what physics has come to describe by an entirely different route. This is not validation. The contemplatives did not prove what physicists have measured. The physicists did not confirm what the contemplatives taught. The 2 inquiries proceeded independently, with completely different methods, and the parallel between their results is structural, not evidentiary. The languages are different. The methods differ. The architecture is the same. 4 traditions, in particular, are worth attending to with care, each named carefully, each held with the hidden teaching at the center, rather than the comfortable surface that has circulated in popular accounts. None of these traditions is what most readers think it is. The first arose in India in the 2nd century of the Common Era. The figure was a Buddhist monk named Nagarjuna. The school he founded is called the Middle Way, Madhyamaka in the original Sanskrit. The principal text is a treatise called The Fundamental Verses on the Middle Way, composed in approximately the year 150. It is one of the most rigorous works of philosophy ever written. It is also one of the most difficult. What Nagarjuna did was strange. He took the central concept of Buddhist philosophy, emptiness, sunyata, and refused to let it become a doctrine. He refused to let it become a thing. He refused to let it become an answer. The popular version of emptiness, the version that has circulated in the West for 100 years, teaches that emptiness means everything is illusion, or that nothing really exists, or that all is one. Nagarjuna taught none of these things. What he taught was more precise and more demanding. He taught that nothing has intrinsic nature. A chair is a chair only in relation to the floor that holds it, the body that sits on it, the wood it was made from, the carpenter who shaped it, the conventions of the language that names it. None of these conditions is intrinsically the chair. Take away any of them, and the chair is not there. The chair has no chairness of its own. Its existence is purely relational. This is not nihilism. Things exist. The chair holds your weight. The point is not that the chair is unreal. The point is that the chair is real in a particular way that is not the way classical metaphysics has assumed. It is real as a node in a web of dependent relations, not as an independent substance with its own being. Nagarjuna applied this analysis with what the tradition calls the four-cornered demolition. He took every possible position about the nature of any phenomenon. The phenomenon exists. The phenomenon does not exist. The phenomenon both exists and does not exist. The phenomenon neither exists nor does not exist. He demolished all four positions, one by one, with rigorous logical arguments. What was left was not a fifth position. It was the recognition that the categories of being and non-being are themselves dependent constructions, useful for certain purposes, useless for the deepest question. What the lineage transmits, and this is the part that almost no popular account preserves, is that the recognition of emptiness is not the achievement of a state. It is the recognition of what was already the case. The chair was never substantial. The categories were never adequate. The demolition does not change the world. It changes the looking. The popular version of emptiness is more comforting. It says that since everything is empty, nothing matters. Or it says that since everything is empty, everything is one. Both versions miss what Nagarjuna actually taught. Emptiness does not erase things. It describes their mode of being. And emptiness is not unity. The four-cornered demolition rules out unity as firmly as it rules out separateness. Whatever the world is, it is not one and it is not many. Both categories are dependent. Both fail at the foundation. What Nagarjuna articulated in the vocabulary of 700 verses of dialectical logic is the same architectural pattern that Bell's theorem made experimentally manifest 18 centuries later. The pattern is this: things do not have the independent existence that classical intuition assigns them. Their properties are not tucked inside them, waiting to be discovered. Their properties are constituted in their relations to other things and to the conditions under which they are observed. This is not metaphor. The Bell tests show that the correlations between distant particles are stronger than any locally real assignment of properties could produce. The particles do not have, in advance of measurement, definite values for the quantities the experiment reveals. Their values are constituted in the act of measurement, in relation to what is asked. Nagarjuna would have recognized the pattern immediately. He would have rejected the metaphysical conclusion that the particles must therefore have substantial existence elsewhere, in some hidden domain. He would have said that the question is malformed. The particles are empty of intrinsic nature. The web is what is. The nodes are temporary, contingent, dependently arisen. This is not to say that Nagarjuna anticipated Bell. He did not. He was not doing physics. He was performing a philosophical analysis from within a meditative tradition, with goals of his own that had nothing to do with measuring photon polarizations. The languages differ. The methods differ. What is striking is that two completely separate inquiries arrived at the same structural recognition, that things are not what classical thought took them to be, and that the relational structure is more fundamental than the substantial one. The map and the territory are not the same, but the maps, drawn from different continents, look strangely alike. There is an image in the tradition, used many times in different contexts, of a chariot. A chariot is a chariot only when the wheels, the axle, the frame, the yoke are assembled in a particular configuration. Disassembled, the wheels are not the chariot. The axle is not the chariot. No part of the chariot is the chariot, and yet the chariot rolls. This is what emptiness names, not the absence of the chariot. The presence of the chariot as a structure of relations, not as a substance. The Bell tests, viewed from this distance, are the chariot demonstrating, in the language of correlations, what the chariot has always been. There is a development of this insight that occurred 5 centuries later, in China, that took the relational picture and gave it a structural precision that Nagarjuna's verses had only gestured at. The figure was a Buddhist monk named Fazang. The century was the 7th. The school he led under imperial patronage was called the Flower Garland School, Huayan in the original Chinese. The principal text is the Flower Garland Sutra, a vast compendium translated into Chinese in stages over several centuries. Fazang's contribution was to extract from this sutra a precise structural analysis of how things relate to each other, and to demonstrate it to his patron, the Empress Hu Zetian, with a famous physical experiment. The experiment was a hall of mirrors. Fazang had a small room constructed with mirrors on all 6 surfaces, 4 walls, ceiling, floor. In the center of the room, he placed a single statue of the Buddha and a lit candle. The Empress entered the room and saw the statue reflected infinitely in all directions, each reflection containing all the other reflections, each reflection of a reflection containing all the others again, down to the limit of what the eye could resolve. This, Fazang said, is the structure of reality. The image is now known by its Sanskrit name, Indra's net. The popular description is that it is a vast net of jewels, with a jewel at each knot, and each jewel reflects all the other jewels. This is correct as far as it goes. What most popular accounts miss is the precise structural claim Fazang extracted from the image. The claim is not that everything is one. The claim is that each thing contains the totality of all things in their relations, and the totality is constituted by the interpenetration of the parts, not by their dissolution into a single substance. The technical term Fazang used is the unobstructed interpenetration of all phenomena, Shishiwu AI. The structure has levels. There is the underlying nature shared by all phenomena. There is the level of phenomena. the distinct appearances of particular things, and there is the relation between them, in which each individual phenomenon expresses the entire underlying nature without losing its individuality, and the underlying nature is present in each phenomenon without being exhausted by any of them. Fazang demonstrated this with the mirrors. The Empress understood. The popular version of Huayan teaches that all is one. This is precisely what Fazang did not teach. The Empress, viewing the Hall of Mirrors, did not see one thing. She saw the statue distinctly. She saw each reflection distinctly. She saw the way each reflection contained the others without becoming them. The structure is not unity. It is mutual interpenetration with preserved distinctness. The popular phrase "all is one" collapses what Fazang spent his career articulating, that the parts remain themselves precisely in the way they contain each other. Unity would be a flattening. The structure is richer. The structure is closer to a hologram than to a melted ingot. This is the same architectural pattern that emerges in two of the strangest results in contemporary physics. The first is the holographic principle, developed in the 1990s by Gerard 't Hooft and Leonard Susskind. The proposal that the information content of a region of space can be encoded on its boundary, that the three-dimensional volume is a kind of projection of two-dimensional data. The second is the proposal we have already touched on, that entanglement and space-time geometry may be the same thing. The conjecture that the connections between entangled particles and the connections through space-time are not two phenomena, but one. In both cases, the parts of the world are not isolated. They contain, in some precise sense, the structure of the whole. The whole is not a separate substance. It is the pattern of relations that the parts together constitute. Fazang did not have the holographic principle. He did not have the wormhole entanglement conjecture. He had a hall of mirrors and a lit candle, and an empress whose attention he held for one afternoon. What he showed her, in the language available to him, is recognizable in the language available to physics now. The architecture is the same. This is structural recognition, not validation. Fazang was not anticipating modern physics. The Huayan school was articulating a philosophical vision rooted in meditative experience and Buddhist metaphysics. Its goals were not predictive. It did not seek to measure anything. The fact that the structure it described turns out to be useful for thinking about results in quantum gravity is a fact about the structure, not a fact about Fazang. The convergence is architectural. The two inquiries are independent. In the version of the story preserved in the Huayan commentaries, the Empress is said to have left the Hall of Mirrors in silence. She did not speak about what she had seen. The texts do not record her response. What is recorded is that she continued, for the remainder of her reign, to fund the school and to honor Fazang as her teacher. The recognition was wordless. It was the recognition of a structure that the room had revealed to her, and that her own existence, and her empire, and the petitioners outside the palace, and the sky above it, had always been participating in. The third tradition arose in the 12th century in the Islamic West. The figure was a Sufi master named Ibn Arabi, born in Andalusia in 1165 and later resident in Mecca and Damascus. His principal work is a vast text called the Meccan Revelations, composed across 30 years and running to thousands of pages. He is widely considered, even by those who disagree with his teachings, the most sophisticated metaphysician the Islamic tradition has produced. The orthodox religious authorities of his own time, and of every century since, have had a difficult relationship with his work. the reason is instructive. Ibn Arabi's central teaching is called the unity of being, Wahdat al-Wujud in the original Arabic. The popular gloss of this phrase is that God is everything, or that everything is God, or that there is no real distinction between creator and creation. These glosses are not what Ibn Arabi taught. What he taught is more precise and more demanding. He taught that being itself is one, but that being manifests through an irreducible multiplicity of forms, none of which exhausts it, all of which together do not exhaust it either. The forms are what he called determined being. The source is undetermined being. The relation between them is not identity. It is not separation. It is something the tradition has a specific term for, and the term is the heart of the hidden teaching. The term is the isthmus, barzakh. The barzakh is the intermediate domain that is neither pure source nor pure manifestation, but the boundary at which the source becomes the forms without ceasing to be the source. The barzakh is not a place. It is the ontological structure of how being passes from undetermined to determined. And there is a further hidden teaching, more carefully transmitted. It is called the presence of imagination, Hadrat al-Khayal. In Ibn Arabi's metaphysics, imagination is not a psychological faculty. It is an ontological category. It is the level of reality where forms exist in a way that is more substantial than concept and less substantial than physical matter. It is the level of reality where being actualizes itself in particular configurations before those configurations become fixed in the world of bodies. This teaching is not exotic. It is technical, and it is the reason the Orthodox tradition spent 6 centuries trying to suppress or sanitize Ibn Arabi's school. The doctrine made claims about the structure of reality that the surface religion could not absorb without dissolving its own categories. There's a phrase that has become common in contemporary spirituality, often presented as if it had ancient warrant. The phrase is that consciousness creates reality. The phrase is taken to mean that what one thinks, one experiences, that what one focuses on, one manifests, that the world is the projection of the mind and the mind can shape it. Ibn Arabi taught none of this. What he taught is the opposite of this in a precise way that matters. In Ibn Arabi's metaphysics, the individual human consciousness does not create reality. The individual human consciousness is itself a manifestation of being, one form among innumerable forms in which being expresses itself. The imaginal realm is not the personal imagination. It is an ontological level prior to personal psychology, in which being takes shape. The personal mind does not control it. The personal mind is, in a sense, controlled by it, or more carefully, participates in it without being its origin. The contemporary phrase consciousness creates reality is, when looked at carefully, a metaphysical claim of enormous arrogance. It places the individual psyche at the foundation of being and credits its preferences with cosmic efficacy. The traditions did not teach this. Ibn Arabi did not teach this. The Buddhist school that is most often cited in support of the phrase did not teach this either. What these traditions taught is that the line between consciousness and what consciousness encounters is not as clean as classical thought has assumed, but the dissolution of that line does not produce a magical self. It produces, when followed through, the disappearance of the self that was supposed to be doing the creating. This is the actual teaching. It is not what circulates. It is, in fact, far less comforting than what circulates. The popular version offers control. The actual teaching offers something closer to the loss of the position from which control would be exercised. The parallel to physics here is precise and worth naming carefully. what Ibn Arabi calls the barzakh, the isthmus between undetermined and determined being, has the same structural position as what the quantum measurement process occupies in the formalism. The wave function, before measurement, is in a state that is not yet any particular outcome. It is a structure of possibilities. The measurement, in some interpretations of quantum mechanics, particularly cubism and the participatory universe of John Wheeler, is the event in which the undetermined becomes determined. The barzakh is the metaphysical name for that transition. The measurement problem is the physical instance of it. This is not analogy. It is structural recognition. Ibn Arabi did not have the quantum formalism. The cubists do not draw on Ibn Arabi, but the architecture they articulate, that being passes from undetermined to determined through a process that is not separate from the asking, is the same architecture. The languages are different. The methods differ. The structure is the same. Ibn Arabi was a Sufi mystic working within Islamic metaphysics. He was not predicting quantum mechanics, and quantum mechanics does not confirm his metaphysics. The convergence is structural and partial. There are claims in his system about the divine names, about the hierarchy of being, about the relation of revelation to ontology, that have no analog in physics and were never intended to. What is parallel is the recognition that the actualization of particular forms from a wider possibility space is the central event of being, and that this event is not separable from the perspective that participates in it. There is a passage in the Meccan Revelations where Ibn Arabi writes about a sleeper waking in the night. The sleeper rises, looks at the room, and for a moment cannot tell what is dream and what is waking. The room is the same. The body is the same. The difference between dream and waking is not a difference in the contents. It is a difference in the relation between the perceiver and the perceived. Ibn Arabi does not resolve the moment quickly. He sits with it. He writes about it for several pages. The room you are in, he suggests, is closer to that uncertain moment than the categories of dream and waking can capture. The barzakh is always present. It is the structure of what is. The fourth tradition arose much earlier in China, beginning in the 4th or 5th century before the Common Era. The principal text is the Tao Te Ching, traditionally attributed to a figure named Laozi, a name that means simply old master and may or may not refer to a single historical person. The text is brief, 81 short chapters, often only a few lines each. It is, alongside the Bible and the Bhagavad Gita, one of the most translated books in the history of human civilization. It is also one of the most consistently misread. The reason for the misreading is not that the text is unclear. The reason is that the text is read, almost always in the West, through a single interpretive layer that obscures the depth of what is actually being said. To understand the Tao Te Ching as the tradition itself reads it, two commentaries have to be distinguished. The two commentaries produce two radically different texts, even though the words on the page are the same. The first commentary is by Wang Bi, a brilliant young scholar who died in 249 of the Common Era at the age of 23. Wang Bi's reading is metaphysical and ontological. For Wang Bi, the Tao, the way, is the nameless ground of being, the source from which all named and determined things emerge, and to which they return. The first chapter of the Tao Te Ching, in Wang Bi's reading, is a treatise on the structure of being. The Tao that can be named is not the eternal Tao. The named is the level of determinate beings. The unnameable is the level prior to determination. What lies between is the structure of how the unnameable becomes the nameable. The second commentary is by Heishang Gong, a more obscure figure of the Han Dynasty, probably the 2nd century of the Common Era. He Shanggong's reading is practical and physiological. For He Shanggong, the Tao is a force that circulates in the body and the cosmos, and the Tao Te Ching is a manual for cultivating its flow. The same 81 chapters become, in his commentary, instructions for inner cultivation, for breathing practice, for the regulation of vital essences. Both readings are old, both have been preserved. The He Shanggong reading dominated the popular and religious Taoism that developed through the subsequent dynasties. The Wangbi reading has been more influential in the philosophical tradition. Almost no contemporary popular treatment of the Tao Te Ching distinguishes between them. The text most readers encounter is a flattening that draws unconsciously from both, without acknowledging that they describe different Taos. The popular Taoism that has circulated in the West for several decades inherits primarily from a softened version of the He Shanggong reading, stripped of its physiological technicalities, supplemented with vague references to flow and balance, and used as a kind of universal solvent for the difficulties of modern life. Go with the flow. Be like water. Find your Tao. The phrases are pleasant. They are not what either Wangbi or He Shanggong actually transmitted. The He Shanggong tradition was a precise system of inner cultivation with specific exercises and well-defined goals. The Wangbi tradition was a metaphysical analysis of the structure of being. Neither of them was a general invitation to relaxation. Both of them had hard demands. Both of them required, in different ways, the dismantling of the self that wanted to do the going with the flow. The structural parallel to physics, taken from the Wangbi reading, is striking. The Tao that can be named is not the eternal Tao. The nameable is the level of determinate forms. The unnameable is the level prior to determination. What lies between is the structure of how the unnameable becomes the nameable. This is, in different vocabulary, the same architecture that the quantum vacuum exhibits in field theory, a substrate that is not nothing, that contains the structure from which determinate particles emerge, that is not itself any particular configuration but the source of all configurations. The vacuum is not empty. It is the unnameable, in the sense that no particular set of measured quantities exhausts what it is. The particles are the named, the determinate, the actualized. The boundary between them is what physics calls the act of measurement, and what Wangbi calls the relation between the nameless and the named. This parallel can be drawn even more precisely. The cosmological constant problem, the discrepancy between the vacuum energy that field theory predicts and the value cosmology measures, is, in its structure, the question of why the unnameable manifests itself in this particular way and not in another. The first chapter of the Tao Te Ching could have been written as a commentary on the problem. It was not. The convergence is architectural. The Taoists were not doing quantum field theory. The quantum field theorists are not doing Taoism. The Tao Te Ching is a contemplative and practical text rooted in early Chinese metaphysics with its own purposes that have nothing to do with predicting particle behavior. What is shared is the recognition that the world of determinate forms is not self-sufficient, that it emerges from a level the determinate forms cannot themselves describe. This recognition is older than physics. Physics has, in its own language, re-arrived at it. There's a passage in the Tao Te Ching, in chapter 40, that consists of only 2 lines. The first line says, "Return is the movement of the Tao." The second line says, "Yielding is its function." The lines have been translated countless ways. Wangbi reads them as a description of how being moves. Every determinate thing returns to the undetermined source, and the movement is yielding rather than forcing. The vacuum, in quantum field theory, exhibits exactly this structure. Every particle that emerges from the vacuum returns to it. The constant emerging and returning is the basic pattern of what is. 4 traditions, separated by oceans and centuries. None of them did physics. None of them confirmed physics. None of them needs physics to validate what they articulated within their own terms. And yet, the pattern that emerges from all 4 is the same pattern. Things do not have the substantial independent existence that classical thought assigned them. The parts of the world are constituted in their relations, not in their isolation. The world of determinate forms emerges from a level that is not itself any particular form. The act of asking is not separate from the act of answering. The categories of being and non-being, of self and other, of one and many, are useful at the surface and inadequate at the depth. This is not coincidence. It is also not proof. The contemplatives were not running experiments. The physicists are not running practices. The 2 methods of investigation are radically different. One introspective and silent, the other instrumental and collective. And they have arrived, by routes that did not cross, at descriptions of reality that share an architectural pattern. What this means is not yet clear. There are possibilities. It could mean that any sufficiently careful inquiry into the nature of what is, conducted patiently enough by enough careful minds, converges on the same structural recognition, because that recognition is the structure of what is. It could mean that the convergence is a fact about the human cognitive apparatus, that whatever method is applied, certain patterns of organization are the only ones careful attention can land on. It could mean something else, something neither possibility captures. The honest position is that no one has resolved which of these is correct. The convergence is real. Its explanation is open. What remains, after the foundation has been built, and the deepening mystery has been entered, and the older voices have spoken, is the slower work of asking what any of this is for. Not in the sense of utility. There is no utility. In the sense of how to stand in front of it. The structure has been laid out. The parallel has been drawn. The disciplines have been preserved. And the question that opened all of this is still open. The world is quantum. The asking continues. The asking has always continued. So what does all of this mean? Not for physics. We know what it means for physics. The mathematics will continue to work. The measurements will continue to confirm. The interpretations will continue to disagree. The work, by whatever name, will go on. What is at stake here is something prior to that. It is the question of what to do with the recognition, not in the sense of action, in the sense of standing. For 125 years, physics has been telling a story that has progressively dismantled the classical picture of what reality is. For 2,500 years and longer, certain contemplative traditions have been telling, in their own languages, a structurally similar story. The two have now arrived at a place where they can be set beside each other, and the architecture compared. What remains after the comparison is to be honest about what has actually been shown, what has been suggested, and what still has not been answered. The work, taken honestly, is not to produce a conclusion. It is to settle, with as much precision as the question allows, into the ground of what is actually known and what is not. The settling is the work. This settling is more demanding than it sounds. The popular versions of both fields offer easier landings. The popular physics says, There is nothing strange here, only mathematics that happens to work. The popular spirituality says, everything is connected, everything is one, everything is well. Neither of these is the actual position. The actual position is harder. The actual position requires the holding of distinctions that the easier versions collapse, and the acknowledgement of mysteries that the easier versions cover. The actual position is the open ground. What is established is the empirical structure. This is not in dispute. Bell's inequality has been tested under loophole-free conditions and in cosmic tests, and it has been violated in every test. The world is not locally real in the classical sense. One of the assumptions that classical physics took for granted, that objects have definite properties before they are measured, that signals cannot exceed the speed of light, that experimenters freely choose what to measure, that there is a single observer-independent reality, has to give. Which one is open? That one of them gives is no longer open. Quantum mechanics has never failed an experimental test. The mathematics has been used to predict the behavior of atoms, the structure of chemical bonds, the operation of every transistor and every laser ever built, the behavior of stellar processes, the precise color of light emitted from particular atomic transitions to 14 decimal places. The agreement between prediction and measurement is the most precise agreement that has ever been achieved between human theory and physical observation. This is not philosophy. This is data. Decoherence is established. The mathematics is rigorous. The experimental confirmations are clear, and we understand why the wave-like properties of large objects are not observed in everyday experience. What is observed at the scale of bodies and rooms and tables is explained in mechanism by the rapid environmental entanglement that the decoherence framework describes. Decoherence has reduced the measurement problem. It has not solved it. The Frousiger-Renner theorem is established. Within the standard assumptions of quantum mechanics, no single observer-independent reality is consistent with the universal applicability of the formalism. The theorem has been generalized. It has not been refuted. The reconstructions program has established a partial but striking result. Quantum mechanics is, given a small set of operational principles about information, very nearly the only consistent theory possible. The strangeness of the quantum world is not arbitrary. It follows from principles that any sensible theory of information would have to satisfy. And what is established beyond physics is structural. Four contemplative traditions, working independently for many centuries, arrived at descriptions of reality in which things are not the substantial objects of classical metaphysics, in which the relational structure is more fundamental than the parts, in which the act of asking is not separable from the act of answering, and in which the categories of being and non-being, self and other, one and many, are useful at the surface and inadequate at the depth. That this convergence exists is established. What it means is not. You have perhaps sat in a room and noticed for a moment that the room was not as separate from you as it appeared. The noticing was not a doctrine. It was a momentary recognition. The recognition has, in its own way, been worked out across centuries by people who did not know each other, and across decades by people who did not know those who came before. The recognition is real. What it is recognition of is more difficult to say. What is suggested by the evidence and by the structural convergence is harder to state without overreaching. The evidence points in a direction. The direction is not yet a destination. The evidence suggests that the world at its foundation is not made of substantial things with intrinsic properties standing in classical relations. It is made of something else something more relational, something for which information may be a better word than substance, something that the act of observation does not passively register, but somehow participates in. The Reconstructions program suggests that this relational, informational structure is not arbitrary. It is forced by reasonable principles about how distinguishable things can compose with each other and remain distinguishable. The participatory interpretations suggest that the standard separation between observer and observed is not a feature of the world, but a feature of a particular way of describing it. The contemplative convergence suggests that this same structural pattern, non-substantiality, relationality, the inseparability of observer and observed at the foundation, the emergence of determinate forms from an undetermined substrate, has been independently recognized by careful introspective investigation for at least 2,500 years. The recognition was not formulated in mathematics. It was formulated in dialectical analysis, in metaphysical commentary, in meditative practice, in poetic image. The languages are different. The structure is the same. What this convergence suggests is that the structural recognition may not be an artifact of any particular method. It may be the shape that careful attention, applied long enough to the question of what is, lands on. The shape may be a fact about the world. It may be a fact about cognition. The evidence does not yet distinguish between these. There is one further suggestion, more tentative. It is that the question, why is the world quantum, asked at the deepest level, may not have a meaningful answer in the form the question expects. The question assumes that there is a world with a property of being quantum that could have been otherwise. The Reconstructions program suggests that this assumption is not quite right. If the world is quantum because consistent informational principles force it to be, then the question why is the world quantum becomes the question, why is information what it is? And that question, taken seriously, dissolves into the older question of why there is anything at all in the structure we recognize as anything. The older question has not been answered by physics. It has not been answered by the contemplatives either. They have both worked at the threshold of it. These are suggestions. They are not proofs. The evidence is strong enough that ignoring it would be intellectually irresponsible. The evidence is not strong enough that asserting it as fact would be intellectually honest. The position of suggestion is the position of someone who has looked carefully and is reporting what the looking has shown, without claiming that the showing is final. What remains genuinely unknown is more important than what has been suggested. The unknown is where the deepest part of the work still lies. The measurement problem is unknown. The mathematics describes two incompatible dynamical rules: the smooth evolution of the wave function and the sudden selection of outcomes in measurement, and provides no account of how the two rules relate. The major interpretations of quantum mechanics are different answers to the unsolved problem, and the choice between them is not empirical. After 90 years, the field has not converged. The honest assessment is that the question of what actually happens when a single outcome appears in the world is open. Anyone who tells you it is closed is selling something. The fundamental ontology is unknown. Whether the wave function describes something real in the world, or whether it describes only an agent's information about what the agent will experience, is not resolved. Whether all the branches of the universal wave function exist, or only the one we observe, is not resolved. The mathematics is silent on this. The interpretations divide on it. The experiments do not distinguish between most of the serious candidates. What information is at the foundation is unknown. The Reconstructions program treats information as primitive. What information is, in its turn, is not asked. There is an open question about whether information is a feature of the world or a feature of the relationship between the world and any agent in it. This is an open question. It may not have a single answer. The cosmological constant problem is unknown. The vacuum energy that quantum field theory predicts and the vacuum energy that cosmology measures are separated by a factor larger than any factor in human knowledge. Something fundamental is missing. What is missing is not known. The reconciliation of quantum field theory with general relativity is unknown. The two most successful theories of 20th century physics are mutually inconsistent in their fundamental structures. The work of finding a theory that contains both is ongoing. None of the proposals has been confirmed. What the contemplative recognition means at the level of what is, rather than at the level of human cognition, is unknown. Whether the convergence across traditions reflects a feature of reality or a feature of the structure of careful attention is a question that the convergence itself cannot answer. No method exists at present that could, and why there is anything at all is unknown. This is the oldest question. It has not become less open with the progress of physics. It has become, if anything, more sharply focused. The honest position is that the question why there is something rather than nothing has not received a satisfactory answer in any tradition or any field, and the careful inquirers in both fields have, after lifetimes of work, mostly fallen silent on it. This is the open ground. It is the part of the work that no one has finished, and that probably no one will finish in the lifetime of anyone now alive. There is a careful objection to everything that has been said, and the objection has to be named. The objection from the materialist side is that the structural parallel between physics and the contemplative traditions can be overread. Structural similarity is not identity. The traditions were doing introspective philosophy rooted in religious frameworks with their own goals and their own technical machinery. The physicists are doing experimental science with mathematical formalism. To map one onto the other is, on this view, to commit a category error that the surface of the parallel obscures. The careful materialist would say that the convergence may be no more than a fact about human pattern recognition. Any sufficiently long inquiry, conducted by minds of the kind humans have, will tend to produce certain structures, and the apparent convergence is the residue of that cognitive constraint. This is a legitimate objection. It cannot be refuted by the existence of the parallel alone. The objection from the strict contemplative side is the mirror image. It is that physics has nothing to add to what the traditions already worked out, and that drawing parallels between the two is itself a kind of subtle materialism, a treatment of the contemplative insights as needing scientific imprimatur, which inverts the actual hierarchy these traditions claim. The lineage holders would say that they did not need quantum mechanics to know what they know. The recognition does not depend on the apparatus. The apparatus does not validate the recognition. This is also a legitimate objection. It cannot be dismissed by pointing to the experimental data. Both objections are correct in what they affirm. Both are limited in what they deny. The materialist objection correctly notes that structural similarity is not proof of identity. It is mistaken if it concludes that the similarity is therefore meaningless. The contemplative objection correctly notes that the traditions stand on their own. It is mistaken if it concludes that nothing is gained by noticing that physics has independently arrived at structurally similar conclusions. What the open ground allows is to hold both objections without collapsing into either. To take the convergence seriously as a fact that requires interpretation, without yet knowing what the right interpretation is, to preserve the distinction between methods without flattening their results into a single discourse. This is harder than either of the simpler positions. It is the position the evidence actually supports. There is one more thing to say, and it has to be said gently because the language strains under it. You have perhaps stood at this question yourself, not in a laboratory, not in a monastery, in the quiet of an ordinary evening, in the moment between sleep and waking, in the surprise of a coincidence too precise to be entirely chance, in the recognition that arrives sometimes without summoning, of a depth beneath the surface of things that the official accounts of the world do not quite include. These moments are not proof. They are not visions. They do not validate any particular doctrine. But they are not nothing either. They have a quality the materialist account has had a difficult time explaining, and they have, across cultures and across centuries, been one of the consistent reports of careful human experience. The contemplatives described them in their own languages. The physicists rarely speak of them in public, but often speak of them in private. There is a particular kind of quiet that working physicists fall into when the conversation in the late evening turns to what the equations are about. What can be said about these moments, with the discipline that has been held throughout, is this: they are consistent with the structural picture that the careful inquiries have converged on. They are not consistent with the classical picture in which the inside and the outside are sharply separable. They suggest that the participation the careful inquiries have both circled is felt, sometimes, as participation by particular human beings in particular evenings. The suggestion is not the same as a confirmation. The recognition is not the same as a theory. But the recognition, when it arrives, is allowed to be part of what is real. You do not have to do anything with it. The structure has been described. The convergence has been noted. The mystery has been preserved. What remains is the ordinary continuance of life, in which whatever has been articulated here continues to operate whether or not anyone is paying attention. The world is what it is. The asking has its own life. The recognition that has arrived does not require allegiance. It only requires that the door, once opened, not be forced shut. There's no more to say. The structure has been laid out. The parallel has been drawn. The disciplines have been kept. The honest position has been named. The objection has been held. And the ground that remains, after all the laying and all the holding, is the same ground that was there before any of it began. There are two silences that have been mentioned in the slow walk. The first is the silence that arrives when a calculation closes, and the one who has worked the calculation knows the answer is right, and does not know what the answer means. The second is the silence that arrives at the end of a long sitting, in which the question itself dissolves, and what is left is not an answer. These two silences are not the same silence. They may be neighbors. They may, in the very deepest places, be the same room entered through different doors. The room is the room you are in. The body is the body that is breathing. The breath that is moving is the breath that has been moving without instruction since long before the asking began. The asking is here. The world is here. The strange relationship between the asking and the world is the ordinary fact of this evening as it is. A long time ago, a chair was a chair only in relation to the floor that held it. A net of mirrors reflected itself infinitely in its own reflections. A sleeper woke in the night and could not tell, for a moment, the difference between dream and waking. A nameless source flowed into named things, and the named things flowed back. And in another part of the world, in a quiet hour, a notebook closed and someone looked at the wall, knowing the answer was right and not knowing why. All of these are the same evening. In a sense, the language strains to hold. The breath rises, the breath falls, the asking continues, and whatever is asking, in any of the rooms in which the asking has ever been done, is part of what is asked about. Not separate, not above, not outside. The world is quantum, and whatever is asking why is not separate from the world that does not answer.